Hello and good afternoon, everyone. I welcome you all in our today's Meet the Young Professional webinar series. As you know that we are inviting the non-resident Bangladeshis who were once part of our EEE community in Bangladesh and now have moved abroad for their career. We want to learn from them and learn about their career paths. I'm extremely happy to announce that we have among us today Dr. Nurul Islam. So Dr. Nurul Islam was a student of the Bangladesh University of Engineering and Technology, and then he moved to the Trinity College in Dublin to get his PhD, and before that he went to the RWTH for his master's, and now he's working on a Brain Wave Bank Ltd in Ireland. So he's actively working on interfacing brain with different electrodes and those kinds of things. So I would give the floor to Dr. Islam and learn more about his exciting research and work.
Thank you, Dr.
Sajid.
So thanks everyone for joining today. It's really an exciting opportunity for me to present or being a representative of what we do in the neural world. Yeah, so I'm not gonna waste your time by introducing a lot of stuff. Just let's get into what we're gonna say today. So yeah, Sajid already introduced me, and I'll start with what I do or what I did in my master's thesis. That would actually create a nice introduction about how we are approaching our neural world. So this is not a monster from any Arthurian movie. It's just the back or the rear view of our brain that is showing the visual pathway. So these are our eyes. Not very scary though. And what happens is, like, whenever light is falling on it, we are like, it is passing through the eye and getting on sorry, excuse me, getting on the retina. And our retina is looking like this. You can call it like a sandwich of rod and cone cells, or because I like burgers a lot, I would say it's like a burger-like pattern. You have got like a cheese and all this patty, and then eventually what you get is like the juicy background over here, the optic nerve. What it does is, like, it collects all the information from these cells, these light sensitive cells, and pass this information towards optic chiasma and towards other brain areas, and finally to something we call visual cortex, V1, which is located somewhere over here. And then from there, from this area, all this information are passing in two different directions, either in the dorsal stream, which is going towards the forebrain, or the ventral stream, which is going towards the temporal lobe, or you can see a temporal bone, a bone behind your ear. So it is going along that direction actually. And each of this pathway passes through many other visual areas like V2, V3, V5, many other areas. Visual area empty, and each of these areas has their own role of processing information. For example, the medial temporal region, it is actually processing visual motion. So what is a visual motion? Think about a car moving in front of you, so you can perceive that the car is moving, right? So this is a visual motion, and this motion information is actually processed and further propagated from this area. But whenever we are looking into shape of an object, or whenever we are looking into the color, or we want to recognize some object like a building or like a car, like a whether it is a Tesla car or whether it is a Ford truck, we can actually recognize it through another pathway, which is called a temporal pathway. And V4 is the region which processes this object information. Now, the reason for giving this brief introduction is that every time when we are living every time we are seeing things, we're seeing many things, so many different things. And our brain is actually processing all this information simultaneously. But whenever we are trying to explore how the brain is working, we have to have a controlled experiment. We have to have only one thing going on so that we can actually um, say that what is the effect of that particular stimuli, visual information, and what is the behavioral outcome out of that. So in my master's project, what I worked with was, it's called visual evoked potential. So think of this way, that we have like this kind of checkerboard pattern, um, and then we are showing this checkerboard pattern in a reversal order. So this one is the reverse of this one. And then we have another set of stimuli shown in the screen in front of the participants. And they're saying like, either the checkerboard stimuli or something like a blank screen. And there is something called flash BEP stimuli, which is like either dark or light. There's nothing in between. The interesting thing is that when we record the brain signal after showing all this stuff, they emerge to give different kind of signals. You can see the waveforms over there, recorded waveforms, and they have different shapes. And these shapes, these specific patterns actually give us a lot more information when we dig further. For example, in my master's thesis, what I worked on was like comparing the visual evoked potential. We also call them event-related potential because they're potential generated by the brain for a particular event. So what we compared is like, we took a set of control subjects and a set of schizophrenia patients, and we ran some studies using this pattern reversal stimuli, so this kind of ERP. And what happened is that for the patients, the green line over here, their amplitude, the intensity of this event-related potential or the visual evoked potential, that decreased a lot. We actually recorded from the backside of the brain. Now, every time you watch a movie and you see that, okay, someone is hit, like if you watch a Bengali movie, someone is hit in his forehead and that person got blind, it always doesn't happen actually, because that part of the brain which processes the visual information is behind your back, not in front of your head. So basically we're recording from the very back end of our brain, and this place is called inion, and there is an electrode over there in a standard EEG system, and we're recording the signal from there, and we can see that this signal reduced. Now the next question that it asks is like, okay, where are these signals coming from in the brain? So we do something called source localization. You see all these electrodes over there? Actually, the signals are generated into the cortex of the brain. And what it does, it propagates through everything, like through durameter, through piometer, and then finally through the skin, and then it reaches the scalp, right? That means that this signal was already transformed or in a non-linear or maybe in a linear way by the time it reaches to our electrodes. So what we do some kind of inverse mapping, we call it source localization, to find out the potential sources of this information, of these signals. And as you can see, like this is the location where the signal was the strongest, but also this signal was somewhat propagated to the forebrain, or we call it prefrontal cortex, and also there are other brain regions. We call them parietal lobe or inferior parietal lobule or whatever. So we actually identified 4 different regions in each hemisphere. You can see there are 2 sides of the brain, 2 hemispheres. So there were 4 regions in each side of the brain, and what we try to do, we try to find out the underlying reason for reduction of this signal. And the method that we used there is called dynamic causal modeling. So we have 4 different brain regions. I'm not going to explain all this different stuff because it's very much field specific, but the fact is that they could be connected to each other in so many different ways, like forward, backward. The brain is not working in a one-way process. It sends information to one brain region, and then it receives some feedback. So there is always some kind of like a negative feedback network. And that means, like in our model, whatever the model we choose over here, they always have a forward and backward model and a forward or backward connection between them. And out of all this possible architecture that we explored only for our control subjects, healthy subjects, we found that this model over here, which is showing the connection between these regions, but not between these two, not between the parietal and temporal gyrus. Um, that is the winning model, and that is providing us the architecture of further analysis of what happens when we try to explore the data for our schizophrenia patients. I'm not going to explain all these things for you now, but the summary is that here are the forward connections are shown by the solid line, and the backward connections are shown by the dashed line. And what we found is that this connection, which is shown over here by the orange color, ITG to LG, which is like inferior temporal gyrus to the lingual gyrus, that connection is being affected. That means all the information that is coming to the brain and passed forward through the dorsal stream, which is like the towards the frontal, medial frontal cortex, or through the ventral stream, the forward connections, forwarding of the information was intact, but the feedback that is required to actually stabilize the signal, that is being affected in schizophrenia patients. So this is something like quite intriguing, that like to understand like at what visual pathway this problem is occurring and how this is different in different disease models, whether it is affecting the temporal to visual connection, or whether it is affecting the frontal gyrus or whatever. So this is the way we do computation, we do modeling in our way for EEG signals. And there are many other ways of doing it. It's just one example that I picked up from my work. For my PhD work, what I did, it is something a little bit more interesting, maybe more interesting, I would suppose. So what we did is like, just imagine that you're going from location A to B using your GPS, right? So you can either walk or use your bike or your car, and you're reaching somewhere, right? And you're taking a path which is not directly connected. You're taking some route to go over there, right? Now, think that from your home to your office, you're following one specific path every day. And then all in a sudden, one day you found yourself that that path is blocked. Maybe, for example, in Dhaka, you found that the road is blocked because Wasa is putting a new line, new pipe, water pipe. And yeah, you have to go through another route. So, okay, let's take another route from your source to your goal using another path. Now, when you are here, you're thinking on your way back that, okay, probably I have another shortcut. I have another way to go to my home using a shortcut, or like spending less amount of time. So you're going from there to this one. So this event that is happening over here, it is called path integration. This is very important. So whenever we need to do path integration, or whenever we need to navigate, it means that we have is sort of like a GPS like information in our brain, right? So like the way your Google map would show you, okay, if you go this way, it is going to take 10 minutes. If you go this way, it is going to take 2 minutes more. That means it is always showing you the shortest possible path, right? So to have all this information into our brain, we need to have the representation of this spatial information, and we call it cognitive mapping. And the question is like how this information are represented, stored, or updated into the brain. That is the research of like that my previous lab where I used to do my PhD project. They used to explore all this stuff actually. So how do you do it actually? Because in human it is quite difficult, but for animal it is quite easy. Like animal research is relatively easier than the human research, and we have chosen rat because rat are very exploratory. It is easy to work with them. So what we did, we implanted electrodes into its head to record the electrical activity of the brain. And also we recorded using a overhead camera the traversing path of the rat. I think you can see it clearly from here. Like the rat is moving from here to there, and we are traversing the path here. Now, the problem is that whenever we are implanting this electrode into the brain, there are many neurons surrounding this electrode. That means like each of these neurons, whenever they're activating, and their activation is actually in terms of action potential. So whenever a neuron is active, it generates an action potential, and we also call them spikes. That means we are recording lots of spikes into in one electrode. But the thing is, whenever we are talking about action potential, or the one we usually see, and the one we usually measure are not the same because we are measuring them extracellularly, not from inside our cell. That means that depending on the shape of the electrode, the distance from the neurons, or the orientation with respect to the neuron, you are going to get different shapes of action potentials. So this is something very beautiful. And what we do, we harness this property to extract or to find out which action potential belongs to which neuron, and we call them tentative neuron from these spikes or from these waveforms. Now, once we classify or cluster them or whatever, we use some machine learning algorithm or whatever to classify them. Once we identify that, okay, this particular neuron is belonging to this one, and that means I know the time, at what time they're happening, I can correlate with the location of the animal. And that gives us more information. What kind of information? This is the black lines are the traversing path, and the red dots are the spikes or the action potentials that are happening. And you can see for this particular neuron, the action potentials or the spikes are more along this part of the arena. This is the whole arena where the animal is exploring, and that particular neuron, one neuron is actually activated only here, or it is giving action potentials when the animal is actually here. So what we are doing is like the animal's behavior, we are trying to correlate the behavior of the animal with the neuronal level activities, right? And then we have got another set of neurons that actually fire everywhere, all right? But whenever we are looking into a particular direction of the head direction of the animal, when it's heading to a particular direction, then the firing rate or the number of action potentials is very high towards that direction. I'll show you a live example after one or two slides. And again, there are another set of neurons which are firing periodically. So if we connect their center of mass, then we find a tessellated pattern, trigonometric pattern that creates like a grid-like pattern. So for example, like whenever we are navigating in our environment, in our head, we're actually thinking of a grid-like pattern, and we're saying, okay, take this road, take that road, something like that. So something very similar is happening. We don't know yet how it is happening, but it is creating the coordinate system in a particular environment. Apart from that spatial information, we also have non-spatial information, something like angular head velocity. For example, the animal is moving its head at a particular speed towards a particular direction, and that is affecting the firing rate, so the number of action potentials of a neuron. Again, the running speed is also affecting it. The interesting part of this information, this non-spatial information, is that whenever we are traversing in an environment, in a real life environment, if I run faster, my relationship to the surroundings, landmarks, is changing quite faster. And if I'm going slow, they're changing quite slow as well. That means I also need an update with respect to my environment to reach my goal, right? So that's where these information processing are important. So here I'm going to show you two examples of like the place cell and head direction cell. You'll hear some noises. The noises are actually action potentials that are generated. And the first video is showing that when the animal is here, that particular cell is firing like crazy. Can you hear this sound?
Yes.
Yeah, okay. And let it go to that place once again and you'll hear the sound again. Going there. Amazing, isn't it? And now we're looking into something called head direction cell. So if you're following, whenever the animal is heading towards this direction, it is actually firing crazily. But on the other, whenever it is facing in another direction, it's quite lower. Can you feel it? All right. So those are the examples of like head direction cell and places. So those are the kind of stuff that I did in my master's and PhD. Now, why I did show all this stuff, not about bragging myself, but to raise an important question. In 2016, one of my colleagues, Charlotte Callan, Dr. Charlotte Callan, she is now a chief scientific officer in one of the neuroscience company. And what she asked me actually is that in my lab, there were 7 to 10 postdocs, and I was the only PhD student. All of them had neuroscience background or psychology background. I only had the engineering background. Now, she asked me, what is my role? What is going to be my title? What am I going to be? Am I a scientist or am I going to be an engineer, right? So at that point, I started actually to think about, okay, what am I? I don't have any identity. I'm feeling some kind of like an identity crisis. But no, here is the thing. Whenever you're talking about scientists, their role is quite specific. They explore new knowledge, they explain facts, and they work on knowledge gaps particularly. But engineers, they find solution and they work on mitigating the capacity gap. So there is one knowledge gap and there is another capacity gap. So we are actually providing the capacity gap. And you know, PhD can be very frustrating. So I kind of like built a model for myself of like how scientists and engineers collaborate themselves just for my personal satisfaction, nothing else. So scientists and other professionals come up with problems and they ask the engineers, okay, do you have any solution? Engineers look for the discoveries that the scientists made and they find a solution and they feed it back to the scientists so that they can create more things. Now, how the neural engineers or who the neural engineers are serving? Neurologists, neurosurgeon, neuroscientists, psychiatrists, and psychologists. And what are the kind of services they're going to provide, or what are the objectives of a neural engineer to understand the form and functions of our brain? So you have probably seen a lot of times the MRI images, which is providing us information about the structure of the brain. But then again, saying that now when I'm talking, my speech is going on, like there are some of the area of the brain which are being activated. It's not live, obviously, but I'm just giving an example. And again, whenever we are tapping a finger, whenever we are clicking our mouse, like the way I'm moving my mouse, everything is creating some sort of activity in the brain. So it is also important to understand the function at what area, which area of the brain is doing what. Then again, to repair or restore the functionality, something like pacemaker of the heart, what it does, it creates a series of electrical impulses that are being put into heart, particularly near the Purkinje fibers, if I'm not wrong. And what it does, it restores that neuronal signaling part of the heart and restores the functionality. Or to replace, for example, cochlear implants. So you probably heard about it a lot. So people who are having sensory neuronal hearing loss, they have like the the sound is reaching into their ear, the mechanical wave is there, but the transduction that happens in the cochlea and converts this mechanical action into electrical signal that can be perceived by your brain, that system is damaged. And engineers in collaboration with the scientists, they developed something like this, which is called cochlear implants, that is making this transduction and creating signals that is understandable by the brain. And these are the areas where engineers can contribute actually. I'm just giving a summary here, but I'll go through them, go through each of them later in my slides. So neuroimaging that provides a visualization of structure and functions, and there are many different modalities of how imaging is done. Implanted technology that can be used to record um, neuronal activities or providing drugs into the brain or do some kind of neurostimulation. There's something called functional electrical stimulation that is working towards functional restoration of limbs, for example, in spinal cord injury, neuroprosthesis, again, artificial limbs and stuff, and brain computer interfacing. It is quite a broad area. It encompasses a lot of things, but I would give example in particular to interpreting cognitive or sensory motor actions into machine codes. And okay, start with the neuroimaging. So whenever we talk about imaging, usually it is pictures, right? So what the kind of pictures we're looking at? We're looking at the structural image of the brain. Also, there is something called diffusion tensor imaging. There are other many different imaging techniques. So this one in particular here, it is showing like how the nerve fibers, the axons are actually connected from one brain region to another. So it's providing much more detail of the structure of the brain. And then there is this functional connectivity that I showed a couple of slides ago, which is trying to look at how different brain regions are interacting with each other. Okay, we got the pictures, but the pictures doesn't say everything. We need to look the actions of the brain to understand it better. How do you look at it? We record the electrical activity of the brain. One example was that I said like the EEG signal that we record. Also, there is something called electrocorticogram, which is actually recording directly on the surface of the cortex of the brain, not outside of the brain, I mean not on the skull. And then there is something called implanted recording, where electrodes are actually implanted inside the brain to record. And this kind of implanted recording has two different kinds. Either they're recording extracellularly, like the way I gave an example before, and intracellularly, they're recording the action, true action potentials actually. And depending on what kind of imaging modalities, they are all neuroimaging modalities, and what kind of modalities you're using, their spatial resolution is also defining their temporal resolution. Say, if I am recording EEG signal, I'm probably getting signals in a millisecond scale. But if I'm recording from intracellularly, then I'm getting in a microsecond resolution. information. And again, there is ethical issues plus experimental issues relevant to invasiveness. For example, the EEG stuff, which is from the scalp, that is non-invasive, so it's not gonna do any harm or damage to your brain. But whenever you're implanting something into the brain, definitely it is causing some harm to your brain. So that is also a consideration during the experimentation. So how we are engineers are providing services to them in general. We are providing recording devices, right? And we're helping to identify and design electrodes, or for these many different kind of modalities, they need different storage format for efficient analysis. And then we need to provide them analysis tools. Plus, every time they do the experiment, we also need to collaborate with them so that the data that we get are actually usable. That means we need to also assist them in experiment design. Also, like we also need to do the signal processing, which should be actually part of the analysis tools as well. Now, when it comes to implanted technology in particular, we can do two different kind of stuff. We can do recording that I have just shown, or we do stimulation. When it comes to recording, actually it encompasses a lot of design factors. For recording, it depends on the resolution, like how you are going to design your electrodes. For example, in single cell activity, you need to implant, say here I'm showing a group of 4 electrodes. Each of them are probably 25 micrometer or 10 micrometer diameter. And then what they're doing, they're recording within a 50 micrometer range over here. But if you are putting a very big electrode, it is going to gather or receive information from many neurons at the same time. That means you are not being able to record or identify single unit activity or single cell activity anymore. It has to be like activity of a cell population. Then it's about stability, whether I'm going to record for weeks or months or year or chronically implants, or we're gonna record it for short time, like a day-to-day implants. Because if we are going to put the electrodes for long term, for chronic recording, it means that these electrodes are recognized in our brain as like a foreign body. That means our brain also has some immune cells, which we call glia, and these glial cells will come and attack. They'll try to destroy it, like the way our immune system works. Every time we get a virus or a bacteria, our immune system becomes activated and it tries to destroy the foreign body. So similarly, they will try to destroy it and they will encapsulate it, which means they will increase the impedance or hamper the quality or the stability of the signal that you are recording. Also, it depends on where in the brain you are recording. For example, if you're recording from a cortical column, like from a multiple sites along the cortex, then your electrode design would be one type. But if you want to record only a particular area, say at the tip of or a very localized area, then your electrode design would be another type. When it comes to stimulation, it gets a little bit complicated. We can provide the stimulation in two different forms. First one is optical. So here in this picture, what I'm trying to show is like, obviously it's very vague, sorry for that. It shows there are iridium electrodes. These small square dots are microelectrodes. And there is a waveguide. So the waveguide is providing some sort of like optical stimulation. And simultaneously, these electrodes are recording the brain signals over there. Then, if you want to do some chemical or microfluidic stimulation, your electrode design needs to be a little bit different, because now you need to integrate microfluidic channels so that you can deliver the fluids in a controlled way. Simultaneously, you also need to record from the brain to see what happens whenever you're delivering the drug. That means your electrode and your microfluids must be integrated in such a way. So these are kind of the challenges that we have when you're working with the implants. And obviously, you can see that folks who are interested to work with fabrication technology, it is something quite interesting for them. Not only that, if you are an optoelectronics guy, you can go there. If you are a mechanical guy who would like to work with microfluidics, this can be a field for you. Okay, now let's have a look into the functional electrical stimulation. Consider a person who has got a spinal cord injury, but the brain is intact. That means every time I want to walk through the street, what I am doing in my subconscious mind, I am sending some signal to my leg, to the muscles, through my spine to go somewhere. And I'm seeing an obstacle, I'm changing my mind, and my vision is giving me a feedback. And using that visual information, I'm processing it, and I'm giving my leg a different kind of information so that I can bypass the obstacle. So all these things, although happening very quickly and very subconsciously, but these are happening, right? Now, if a person has this kind of injury, how can we restore their functionality? The theory is very simple. In the same way, like the brain activates the muscles, we can provide electrical signals into the muscles to activate them. So we need to understand how brain is sending, or what is the pattern of electrical signals that are being sent from the brain to the muscles. If we can understand that, then we can devise something that can control and create this kind of stimulator or electrical pulses to control the muscles. And then it means a person with spinal cord injury can still walk with the help of this device, right? Similar example is maybe more practical example, because it is already in use, is urinary incontinence. If you know about this thing, it is like involuntary leakage of urine, and it can be very, it can reduce the quality of life for a person. It can reduce the person's confidence and overall quality of life as well. So what this device is doing is like the bladder is not receiving appropriate signal from the brain, either from the stroke or maybe for some congenital problem. And this device is sending equivalent electrical signal into the bladder so that the urination is now more controlled. And you can actually have an external controller to actually control this device, switch on or switch off this device. So you don't need to always keep it on or keep it off, something like that. And there is something called deep brain stimulation. It is pretty much the same principle. You provide electrical impulses into the deep of the brain to do something amazing that I'm going to show you in the next slide. So let me play the video.
Okay, sir, so a small wire in the brain.
Okay, so what you're seeing in here, the narrator will explain it actually, but what you're seeing, this person has got something called essential tremor. So he cannot actually stop shaking. He's always shaking like this. And what this professor will do, they already have some implants into this person's brain, some firmware, and there is a controller over there, like the pacemaker, and he will switch something on and off. Let us see this video.
Brain, and it's hooked up to this little battery in your chest.
Right.
And now we're able to turn it on, and let's see how it helps the tremors. Okay.
Okay.
Let's do that right now. Hold your hands out. Let's see. Okay, I'm gonna turn it on. That just turned it on. It takes about 8 seconds to kick in.
Oh god, that looks like a magic, isn't it? All right, so you can also watch Professor Andrew Lozano's TED talk, and that's quite interesting as well. And there's another example of like, the previous one was about the deep brain stimulation, but whenever it comes to neurophrosthesis, it is about functional replacements, and we can do it in many different forms, like replacing the sensory functions. For example, the bionic eye. So at the beginning of my presentation, I showed you like how the brain is working, like it is taking some image and it is converting it into electrical signals that the brain understands. So if we can mimic something like this, that you take a camera and you take the pictures in front of you or whatever you're seeing, and you are continuously replicating the signal into something that the brain understands, pretty much the way our retina is sending it, sending to the brain, then we can actually see the world through a camera. Like even a blind person with retinal degeneration or macular degeneration, is some kind of like neuronal degeneration stuff, I mean disease. So if we can do something like this, then even a blind person can see. Again, the cochlear implant is another example of sensory functional replacement. I already told you about that. There is another important thing is like speech to motor neuron conversion. Now, every time I'm talking to you, right at the moment in this talk, I'm saying this kind of sound, like it's quite natural for many of us, right? And why this is happening? Because when I'm thinking to say something, and then in the middle of that, I am thinking like, okay, probably I'm saying it wrong. Let's try it another way. And then I'm saying it in a different way. Now, again, what happens is that my brain is processing some speech, and it has a relationship with the motor neurons that control my lips and whatever, everything that is involved with the speech. And it sends signal to that, and that is then translated into my speech, right? Now, if a person has a stroke and this link that creates the speech to motor neuron transduction or whatever, like the transmission of information is gone, then how could we restore the speech of that person? Okay, if we can record the activity that is going on in the auditory cortex of that person and transmit it outside and decode it, like what he's trying to say, and then use a voice synthesizer or speech synthesizer to mimic that sound, then we can actually read his mind, right? And at the same time, we need to give him a auditory feedback, because like the way we are talking, we are also listening to ourselves. So we need a feedbacks to make sure that whether we're saying it right or wrong. So there are research going on about this real-time synthetic speech production as well. I'm not giving reference to any of them because it will be very much overwhelming to just type out, okay, XYZ et al. And blah, blah, blah. But you can definitely search with the keywords and find all this cool stuff. There is another example of motor neuron functional replacement. As you can see in the title, it says it is a 120 million robotic arm. Obviously, it's quite expensive, but it's quite interesting as well. So let's start over here. Okay, let me give you background. So what happened is that this person lost his arm in an accident, in a road accident, and researchers are trying to give him a biomimetic hand. So like the same way I'm thinking of moving my mouse here, he can do his, move his hand in the same way, like from his thought, from his brain activities.
I used to be a salesman, and in 2005, I was diagnosed with having cancer in my left forearm. It was so aggressive, it just wouldn't even slow down. So in 2008, they amputated my arm just above the elbow. I got a second chance of life. You don't think that doesn't make me happy and give me that much more of a drive? Yes, it does.
You can see that the robotic arm is so realistic. It is using the electromyogram, the muscle action potentials, and it is translating that using, of course, using lots of machine learning algorithm and translating it into robotic hand action. So yeah, there is another example of functional replacement, and it is actually something we can expect in maybe 10, 20, 30 years later. What, like in previous two slides, what we saw is like sensory and motor function replacements, but what about the cognitive function replacement? For example, a person had a stroke and a portion of the brain that performs some executive function is gone. Now what we want to do, we want to replace that with a VLSI circuit or replacement silicon neurons so that it can, like the person can perform similarly or almost similarly like when he was a normal person, like without the stroke or without the damage. So this is something, another aspect of the research in neuroprosthesis. And all these things are already part of the brain-computer interfacing, but there are more about brain-computer interfacing. Sorry for showing lots of videos, but I think they're very cool to watch. So hopefully you are not feeling bored.
At least with movement-based actions, we do that all the time. So you can visualize 1, 2, 3.
Okay, what they're doing here is like this person is wearing a headset from Emotive Technologies, and what he will be trying to do is like vanish an object, a graphic object, just out of his thought.
Go.
So he's getting trained. Training is done.
Okay.
Now we'll give it a try.
Let's try that. Oh my goodness, it's just too good.
It's not there yet.
Losing concentration.
But we can see that it actually works, even though you can only hold it for a little bit of time. As I said, it's a very difficult process to imagine this. And the great thing about it is that we've only given the software one instance of how he thinks about disappear. As there is a machine learning algorithm in this.
So you can see like how cool this stuff can be. And also there are new attempts that's going on. This is one of the very latest paper that published like how transcranial direct current stimulation or external stimulation into the brain. There's another one called transcranial magnetic stimulation. So this kind of external stimulation actually enhances the cognitive performance of the brain. So these are kind of the things that are used for either creating neural prosthesis that I showed you in the previous slides or augmentation of our brain function. Another example of brain-computer interfacing is going to be like this. Okay, so let's think about like playing a game in PlayStation. So what we are going to do, we're going to take an action, we're going to deciding something, and then we are pressing the buttons accordingly. A lot of things going on simultaneously, right? And nowadays the technology has improved, and what they're doing is like they're setting up some sort of camera. I forgot the name of the technology, kinetic or something like that, or kinect. Anyway, so what they're trying to do is like you're dancing in front of the camera, and the personification of you in the game is also dancing. Or you're fighting in front of the camera and that is fighting too. Now, how about if we can translate all of these thoughts into the actions in the game? We call it a neurogaming. And one of the first attempt of neurogaming is called NeuroRacer, where the attempt was to keep the car into its lane and then also to follow the sign or both. And that means like you're using your brain signal, not other in hardware, just to make it into an action or drive something, or maybe drive a car in future. Like the application could be something like this: a tetraplegia patient, like a patient with whole body paralysis. they may try to attempt to drive their car using just wearing some set of electrodes in their head. So that is kind of a thing, cool kind of stuff. Hopefully we will see in a couple of decades. Now, for the moment, their use is mostly on cognitive function, like improving the cognitive function or working memory function or motor function in patients with autism, attention deficit hyperactivity disorder, or Alzheimer's disease, or like people with substance uses. Yeah, and I think like there are significant amount of work going on to like improve the quality of life through neural engineering, through neuroscience as a whole. Now here's a summary of how neural engineers, like engineers working in neuroscience, are contributing. They're creating new imaging or visualization technique, novel therapeutic or assistive technology that they're contributing to. They're creating novel hardware like new electrodes, new analytics, new machine learning algorithm, new ways of looking into the data, and then novel algorithmic development so that they can control those cool robotic hands with the muscle signals, right? Okay, what do you do in my company, in Brain Wave Bank? Not very difficult, but kind of like cool. So this image that you see, this is the conventional EEG system where you wear these headsets and then you are recording using lots of wires. And our company produced this headset, which you can actually wear like a cap, and it will record your brain activity using dry electrodes. So the setup time for this kind of EEG system is like an hour. And after that, you have to wash your head because there are gels put into under these electrodes to improve the connectivity and so on. But in this case, you just plug in and plug out, like wear a cap and open it up. That's it. So that is something we're trying to develop and evaluate and use. Moreover, the kind of tasks, because whenever we need to, as I showed before, like whenever we need to elicit a certain function of the brain, we need to design some tasks so that we can only observe one action at a time. And this is something called pure insertion, because simultaneously we're doing so many things, and this is like we have to maintain one thing at a time to know that the signal that I'm recording is actually coming from that particular event, right? So we have these games developed in such a way that we can, like the user can stay at home. For example, the old patients in Alzheimer's or Parkinson's, they don't need to go to the lab to do all this stuff. All they can do is like stay at their home, wear these caps, play something in their tablet, and all their data will be recorded and sent back to somewhere. Now, I'll give you an example of a classic oddball paradigm. So here you can see that on the left, there is a circular ball, like a circular spot, and there is a rectangular spot. In the next one, there is a rectangular spot and a circular spot. And you can see that these patterns are repetitive. They are standard stimuli. But all on a sudden, you can see that these are very small. Like compared to this one, these shapes are smaller. That means it is odd to this standard collection. And this odd stimuli, we call it oddball paradigm in simple. It creates, okay, basically what happens is like whenever you see something like this, some anomaly like this, you are asked to give some actions. For example, either click a mouse or a button or blink your eye to give a response. And this is the sensory response usually. And there's another component over here, which we call P300, that is representing the decision making. So the decision that you're taking, whether this is same or different, is being reflected by this signal. Now, think about this task and how I can gamify it. In our company, how we are doing it is like we are replacing them by spaceships. So we have got lots of these spaceships, and at any given time, a spaceship has either a good-looking alien or sorry, a good-looking astronaut, or like an ugly alien. And what it is instructed is to tap on either side of the tablet to shoot the alien. So if you tap over the skin of the screen, it will actually shoot the alien. That means you are asked to mimic the task that is happening over here, right? So it is also an oddball paradigm, but it is a gamified version of the lab-based task. And the kind of signal, EEG signal that you record from there is quite comparable to what we see in a textbook P300. So that's the end of my presentation, and I'd like to have some questions now.
Thank you so much. First of all, it's a fascinating field. Whenever I listen to any of the neural engineering or neuroscience talks, sometimes I wonder which one is actually science fiction or which one is actually reality. And particularly the video that you showed, that with mind, he just vanished a thing. It just reminded me, I don't know if you're a Star Wars fan, it's very similar to what the Jedis were doing, just using their mind moving objects or something like that, right?
Exactly.
Yeah, I think we have a question from Aniruddha Rakshit. You can go ahead and unmute yourself and ask the question. I'm not sure if he's having audio difficulty. Let me read out the question for you, Aniruddha. So he asked how we can pre-process any neuro image like MRI or fMRI to combine with this type of EEG data.
Well, I haven't actually worked with dual modality. I have never worked with the fMRI, to be honest. I worked either with the EEG or mostly with the implanted technology. But you can look for toolboxes like statistical parametric modeling, or SPM, or maybe EEG Lab may have some feature to combine those stuff as well, but you have to explore a little bit more because I haven't worked with fMRI myself.
Okay, thank you. So I actually have another question. So I mean, I've been familiar with this kind of work. Dr. Abdullah Arafat. So he's another assistant professor from Buet. So he used to work with a similar type of field. Whenever I used to go to his talks, I used to be fascinated about it, but then I also used to get scared about all the biology and other things. I guess my question is, as an engineer, when you go into a field like interdisciplinary field, what kind of trainings or what kind of background knowledge you need?
Okay, so basically it depends on your type of tasks. For example, if you're working with electrode design, for like giving a very basic example, then definitely you will get some kind of requirements of how your electrodes should function. And that requirements usually come from, say, a partner lab who are working with the neuroscience. And when this kind of collaboration are happening, you mostly need to focus on meeting the requirements of your electrode design, not about like the biology of it. But then again, if you're working with something like what I do, for example, I need to know a bit of the brain structure and which part of the brain is doing what and how. And I was lucky enough that in my master's program, I literally had to study anatomy and physiology, but not always you need to do that. There is no big need for that. So you can just learn whenever you need to learn. It's not something very rocket science or some difficult stuff. You can just say you need to know about the auditory cortex, how it works. You just open up a textbook and read about it, and it's quite easy. Like at this stage, whenever you're planning to do your PhD or your master's, or you are actually like a active researcher, this kind of things usually don't bother much to, like, the learning curve is not that difficult, that steeper, that I would say.
Yeah, thank you very much. Is there any other questions from the audience? Okay, before we conclude the session, I actually want to invite everyone to turn on your webcams. We want to take a group photo with the speaker for this event. And
my camera is in a very weird position, actually.
okay, no problem.
Anyway, I'll give it a try.
Okay. Also, I shared our YouTube page's link. So we are recording this session. I'll first share the recording with the speaker. So he has to approve the recording. So after that, if he approves, we would upload it into our YouTube channel. So please go ahead and subscribe to our YouTube channel if you want to have the recording. Okay.
Thank you, Sajid, for organizing the event, actually.
No problem. It was really a wonderful talk. I think the more problem is when people see neural or biology related terms, they tend to get scared and not.
Oh yeah, they think that a lot of biology is required, but no, not really. Like that's why I showed this part, like the science, how the science and engineering is actually working or interacting with each other. You don't need to get panic. All you need is like, need to know what you need to do. That's it.
Okay. Okay. Now we're going to take the photo.
Okay. Saying hi.
Okay. 1, 2, 3.
All right, we're good to go then.
Yeah, we're done. So
I'd like to thank everyone who attended the session today. And yeah, it is really nice to see a lot of young faces getting interest in neural engineering. It's very encouraging. Thank you very much.
All right. Thank you so much for coming, everyone, and hope to see you all in our next event. So on next Sunday, we plan to invite 3 young professional women who were in our section before. So Dr. Shamima Nazlin, Dr. Neetu Said, and Dr. Faiza Hafiz. And after that, we would invite Dr. Ahmedullaziz Rafi. So he actually worked particularly on brain-inspired computing and neuromorphic computing. So if you're interested, you're welcome to come to both of our sessions. With this, thank you very much.
Take care, everyone. Bye.